Hello, my name is Tyler DiMattima and this is Lab 3, centered around magnetic fields. In this experiment, the problem was really focused upon finding the distance dependence of a bar magnet and also creating a Python model that would allow us to find the magnetic field of a bar magnet at various different angles. The approach was well outlined in the instructions for this lab, and we set up the tape to measure the distances and also download the app to measure the magnetic fields. All this was done by making sure we cancel out Earth's magnetic field so we get more accurate readings for the magnetic field of our bar magnet. After doing this, all we had to do was run the magnetometer in my phone parallel to the bar magnet, and our readings were very accurate. In the end, I found that we were able to actually calculate the distance dependence n and the magnetic dipole moment of this system. These values are highlighted on some later slides. On this slide, you can see the experimental values that I calculated throughout the experiment. On the left, you can find the R vectors that actually represent the distance that the magnetometer was from the bar magnet. And 2 columns over to the right, you can see the average magnetic field values associated with these distances. With all this information throughout experimentation, we were able to make the graph on the right, which is really helpful in terms of this lab because the slope of this line is the distance dependence. Our value was very close to -3, which is the assumed distance dependence due to the equation. This shows that our results were accurate and consistent. After plugging all those values into the Excel sheet and compiling the graph, I was then able to calculate my magnetic dipole moment for the system. I did that by using the equation at the bottom of the screen. The first step to simplifying this equation was realizing that all our measurements were done with the magnetometer parallel to the axis of the bar magnet, meaning that the magnetic dipole dot r hat would just equal the magnetic dipole. I used this knowledge to simplify the shown equation to be the magnetic field equaling mu naught over 4 pi times 2 times the magnetic dipole all over r cubed. Now that I had this equation, I was able to plug in my respective R vectors with their associated average magnetic fields to calculate the magnetic dipole for each of these instances. Averaging these values, I was able to find my average and final magnetic dipole for the system. After having calculated the overall magnetic dipole moment of my system, I was able to start the Python aspect of this lab. And the first step in this was plugging the calculated value into line 24, as shown below. This value is very crucial for our whole code, as it's used in the function defined from line 32 on that calculates the magnetic field at different R vectors. As you can see on this screen, that very function is used heavily in the nested for loop. This nested for loop is used to calculate the magnetic field on perpendicular axes and parallel axes to the bar magnet. I chose to make this a nested for loop so you could actually see how the magnetic field decreases as distances increase. I also placed in this for loop the magnetic field calculation at a 45-degree angle to the top right of the bar magnet. This was placed in the for loop just so you could also see how the magnetic field turns and decreases as distance increases. On this screen, you can see the final product of all that coding, the Python model. In this model, you can see the magnetic field on axis and on perpendicular axes to the bar magnet, as well as at a 45-degree angle to the top right. You can also see here, as I said before, that the magnetic fields decrease as distance increases, and you can sort of see them fade away. On the bottom of the screen and to the right of the screen, you can see the actual calculated values of these magnetic fields, with the values closer to the bottom being the ones that are at a closer distance. As I mentioned before, we had to compensate for Earth's magnetic field in this experiment. We did this by making sure that our phones were on a parallel axis to Earth's magnetic field, making sure that Earth's magnetic field is only read in the y component of the magnetometer. If we chose to instead lay this experiment out at an angle, then that magnetic field would also be contributing in some way to the x component of the magnetometer reading. And this would really make it hard for us to isolate the bar magnet's magnetic field and do all our calculations. This would overall result in the distance dependence and the magnetic dipole moment being calculated incorrectly. Now, if we were to repeat this experiment with 2 identical bar magnets stuck together end to end, then we would observe that the magnetic field recorded would be almost double that of our first run through of the experiment. This would not exactly be double because the R vector for the second magnet would be greater than that of the R vector of the first magnet. It would be greater by a distance equal to the length of the first bar magnet, making the contribution of the magnetic field overall from the second bar magnet being less than that of the first bar magnet, resulting in a less than double magnetic field. Thank you for watching.